Great. So today we are talking about clustering, unsupervised learning. So we talked about, right, we have supervised learning and unsupervised learning and semi-supervised learning and reinforcement learning. I had another plot of them here, right? Let's see if I'm in a good mode. There we go. Okay. So remember what we've been talking about up until now, I guess. We had some semi-supervised learning, right? Because we were dealing with data where we're using, in text, the embeddings we're extracting patterns and essentially labels from the ordering of the words themselves. So we have some information that's inherent in the data without being given a label. But in most of the stuff we've been talking about, we have a classification or a prediction problem where where we're given data X and some actual labels Y, or the right answer that we want, and essentially all our methods are trying to tune the parameters of some function that yields a probability or some other number that helps us use a threshold or some other method to determine this label. So in decision trees, we're grouping data points together and we can take the mean of them or the max of some statistic and get a number that we use for prediction. We can apply a threshold to say if it's above or below some probability, then it's in this class or another. In SVM, we're using kind of the spatial distribution of the points to find lines that divide the points. And then if you're on one side of a line, you're in one class or another. In MAP and MLE, we're using the functional forms of these functions to derive what the optimal parameters would be, and then using that as a predictor of the right value to get our classification or prediction. These are all supervised, right? So we're given all this information. So there is another broad category of problems and algorithms which are called unsupervised, and you've seen a little bit of it already in a way. So PCA, which you've already done, is essentially unsupervised because it's using the structure of the data to find its own information. And but it's a fundamentally harder problem, right? Because we're trying to learn some representation of the data. And we want to find the best representation, but what does best mean, right? It could be best for denoising the data, so instead of cleaning it up and removing stuff, it could be best for coming up with a probability distribution that matches it, so density estimation. Maybe you want to predict what data point will go somewhere, so we could even have interpolation as another problem, right? So you have a bunch of data points, and you can learn models of all these ones, but you want to know, well, what if a point were here? That's a question mark I'm trying to draw. On the x-axis, what would the y be, right? But you don't have one for that area, and I guess if it's supervised, we don't have y's for any of these, right? We only have the x's, and we're trying to predict some other thing. So it's more difficult because we aren't given the answer y to predict, so we're trying to find inherent structure to the data, right? So it's harder to even evaluate. So the lecture the part S lecture, so the lecture that's on YouTube already, is about evaluation of these methods. So once you have a clustering, how do you determine if it's better than some other one? And you can't use accuracy, right? Because we don't know the right answer. And so you have to do things like, well, is it spread out? Is it densely packed? Is it spread out? Is the data well separated? So none of these are as crisp and kind of clear that they're correct as accuracy, but there's a bunch of methods that people have defined for clustering, so you can listen to those ones after we've done through these core 3 kind of approaches we're going to talk about today. I should have a watch here because I really want to make sure I get through them. So semi-supervised are kind of in between, right? So you could say that well, I have methods on the next slide. This is from the Murphy textbook. There's his tree of how machine learning divides up, and so this kind of is getting updated and changed over the years, but at least a few years ago, that's how he saw it. So like we're saying, we had supervised learning. We've already talked about various things you can do here, and we will return to this because all the deep learning we're going to mostly talk about. But we'll talk about about supervised and semi-supervised, because there's many deep learning models that are very good at basically using the data you have to learn and embedding. So the text classification stuff we did was essentially semi-supervised because it's using the structures of the words, right, and their ordering as part of your label, right? Because the neighborhood around you is really the structure you're using, but no one has said, the right answer is this. Essentially, the data contains labels because the right answer for T3 would be what's T4, right? What's the word that follows it? Or at least that's one way to look at it. Fully unsupervised learning, though, is you have no structure. You're just given a bunch of data and you want to know, how they fit together. So customer data or census analysis or market stuff, like I give you a bunch of data points and you say, find me like 3 or 4 useful groups and tell me which one I can send ads to, and you don't know anything about them. That's unsupervised, right? So it's actually fundamentally harder. And reinforcement learning, as I talked about, is kind of a whole different area where you're getting feedback as you go. But for making decisions, you're optimizing and learning. So you do a lot of these things along the way to learn how the world works. But you take your input from the world and then you update your model and you optimize further. So it's a kind of way of doing dynamic learning for control systems or for decision-making systems using machine learning. So my research is in this area, and I have a bunch of kind of projects going in this way, and we have an undergrad course in the summer on it. If people are interested in reinforcement learning, especially as you get through, once we finish through more of the deep learning and you want to do more and you're interested to talk, I'm happy to talk about these things, but I don't know if we'll have time to talk about it in the course, but it's interesting stuff. So today, this is where we're talking about this part, right? So how do we do essentially this? There is another branch of unsupervised learning called association learning. There's also, it's like a big area is association rule mining. That used to be part of this course, but I don't think it's not used as much these days. Although it's used a lot in marketing and customer analysis, because you're basically trying to come up with logical rules that satisfy certain relationships between the data, right? So if you buy, what's the example we always use? If you buy shirts when you're at Walmart, you tend to buy ties, or people who buy rice tend to buy this kind of vegetable or something. So you're trying to find correlations and then use that to predict what sales to give people or something. But there's no one gives you the labels, you're just looking for patterns, right? But it's much more strict than this clustering that we're going to talk about. So the ones we're going to talk about are here, and we're essentially going to talk about these 3 things, specifically these algorithms, I guess, yeah. And there are really 3 completely different ways to deal with this situation where you got to learn some patterns, but no one gave you any labels. So how do you do that? That's the idea. But there's a whole bunch of other areas and algorithms that you could talk about, and we can get into them kind of later after we do these basics. Hopefully that's clear. Okay, so like I said, in unsupervised learning, we want the best representation, but it's hard to define what best is, right? So it's kind of dependent on, I guess, the problem you want. So depending what you want out of your data, you might use a different algorithm, but it also depends on what you know about your data. So we're trying to come up with some representation of the data that's simpler than the data itself, right? So if you, we've already talked about things like that, right? That sounds a lot like what dimensionality reduction is, right? You've got some high dimensional data, like 50 features or 100 features, and then you run PCA or LDA or something like that, and you bring it down to 4 features or 2 features, and you use those to do some plot or do something else, right? So those methods are useful here, and you can basically, all the methods we're talking about today, you could apply PCA first and then do clustering on them, right? So you can use the data directly on a clustering algorithm, but you always could use some dimensionality reduction method first and get some different features, and then run your clustering algorithm and come up with your clusters, which we're going to define in a second, what a cluster is. And I mean, this really, in a way, this applies to almost all of the problems in machine learning. You could always pump it through one of these feature settings first. I know that's always true. Text data might be difficult. But once you have some kind of other representation, these methods often can help. So it doesn't really matter. These algorithms are agnostic to what the data is. You come in with data as features, which is, say, you get data from the census, which gives everybody's, income and school education and where they live and other information about them. And you do some clustering on it to say, what's the grouping of these people and are they similar? If you ran that through PCA first, you'd end up with a small number of features that are unintelligible, but much more meaningful because they are much more representative, because they minimize the amount of variation in each one, right? So they represent the highest dimensions of variation in the data, and then you can run clustering on those. You'd have to always map back to your data points, but you can do that. So that's why we're saying not mutually exclusive. You can do different representations here. So the idea is we're given some data, right? It could be documents, it could be images, it could just be numbers, and we want to divide them into groups, right? And so we're saying groups here. When we say clusters, that's what a cluster is. A cluster is a group of data instances, I guess, if we're calling it that. And so a class is similar to that. We have, when we're talking about classification, right, we have a bunch of data points and we're saying this is a class and that's a cluster. So there's not really any difference between a class and a cluster, other than just the meaning of it semantically as we say it, that if we say I gave you, if these data points are in a class, that means someone gave you the class. So I knew they were all there and they're labeled, right? When I draw a set of points and I say they have a label, I circle them and say, oh, okay, these are data points A, and these are data points B, and these are data points C. You could say these are classes because I told you what their names were, right? If I gave you those same data points and didn't give you any labels, and then you run clustering and come up with shapes like these, they're clusters. You could label them A, B, C, but so there's not really any fundamental difference. I'm not going to pick about, is this a class, is this a cluster? But the algorithms, just when we call them a clustering algorithm or classification algorithm, that tells us that we know the labels, where it's supervised, labels are given to us. We do a training phase because we have these things, we can figure out what the right model is, and then when we get new data points or other data points that were in our test set, we can apply the same structure to that, right? It's easy to evaluate because we know the right answer, and we've talked about all of these now in terms of the standard algorithms that you can use for classification. Of course, neural networks would fit here as well, but they can basically do any of these things. So clustering, we have the same problem. We're given some data points and we want to group them together into meaningful groups, but no one gives an example of meaningful groups. So that's the hard part. You want to organize it. So there's not as much of a training phase. You basically are going to fit, you know, come up with some model on your data, but it's not training in the sense that you're optimizing towards the right answer. You're just going to keep doing it until you decide to stop. So you have to have some optimization criteria that tells you, okay, we've done good enough, right? So we need some measure that says this is a good clustering. And so we'll mention those a bit today, but then there's that online video with a few more evaluation methods to say, like, is this one good or not, right? But usually we're using a notion of similarity, right? So if some data points are similar to each other, then that means they should be in the same cluster, you'd imagine, right? So the same rules apply as they do for classification, that a good clustering is one where the all the data points that are similar or are in the same grouping are together. It's just a way to figure it out ourselves. So I think I've said that enough times now that that should be clear. So what comes next? What other things are in Notion here? So just examples of algorithms we're going to talk about. Yeah, so this idea of similarity of points is going to be very important, and the training phase is going to be different. So it could be, like I said, you're grouping customers or people in a census, but you could have social network, right? So are these people similar or not in some larger network structure? Basically any type of data, you could have the notion of whether two data points are similar and should be in the same group could be dependent on that, right? So if it's a social network, you might be using if they're friends or if they're friends of friends, right? Or where they live. Whereas for customers in a store, you don't know that information, but you might know how often they come to your store and their age and what they bought last time, right? So whatever information you have, you're using that to kind of come up with groups. So you could do it on genes or proteins and try to group them together by similar structures and try to find patterns. So it's a good way to try to understand your domain. The same way we do dimensionality reduction, which I showed you with the chemistry thing for the text data. Actually, we were trying to extract an embedding for the chemistry relationships, and that helps you explore the domain because you can understand the data. So if you didn't know that it was molecules and you already know the periodic table, that kind of thing could be useful, right? And so in clustering, you're going beyond that, not just learning and embedding and then trying to plot it, but you're actually trying to come up with explicit groups and see what they mean, right? So more examples. I've said some of these already. Spatial data, web mining. Yep, so I already said that. So there's a bunch of design issues you have to come up with when you're deciding how to use an algorithm like this, or how to make one. How do you represent the pattern, right? We could just have sets, right? So we can just have sets of points, and that's the kind of default way to think of it, that, you know, some of the data points are in here, and then some of them are in another set, and the idea is you're trying to come up with the setting, the assignment of all the data points to appropriate sets, right? But how do you know how many clusters you have, right? Here I've got 3, but who said 3? Why is that the right answer? And that's actually an issue, because one of the algorithms, k-means, the kind of most popular one we talked about, you have to tell it k is how many clusters it is, and you have to pick that. There's no right answer because it depends on the data. How do we decide to group data together? And how do we assess and interpret the results? So all the plotting and dimensionality reduction methods we have already, we can use for showing the data. But actually in analyzing it, we need some other measures. Okay, so I've already said this a bit already. So we have still our original bunch of data points, and now we're trying to come up with some sets that basically group the points together. And we're going to use our objective function that we define to say that they are good groups and optimize that somehow, like doing it blind, essentially. We're going to have the distance between points, and hopefully I keep this notation constant. Yeah, we use that for the first part anyways. So we have two data points, P and P prime. We'd be saying the distance between those points. It could just be Euclidean distance or Manhattan distance or any of those measures we've talked about before, or cosine distance. But then we'll also have distance between clusters, right? So we haven't talked about this before. We can say, what's the distance between these two sets? And there's various ways you can actually define that, and that defines the first set of clustering algorithms we're going to talk about. Okay, so Alex has a question. What can we include constraints? What would happen if we have a data set without labels, but we know how many labels we have, or some other constraint, like a particular class is only when feature xi is greater than a value? Also, if you have that information, yeah. So anything where you have some information, and technically that would be semi-supervised. So semi-supervised is not a very well-defined field and notion. I'll go back to that slide actually, because I mean, even the reason that the fact that it's called unsupervised and semi-supervised, a lot of times now people call this self-supervised. We're using the data as we were talking about before, like in Word2Vec. So Word2Vec is a good example of that. But truly, another way of getting semi-supervised is like you're given, which is what Alex is kind of proposing, you're given some information, right? Either some data points have labels, or you have some information about every point, but you don't have complete information to call it supervised, right? And so some of the things you're proposing where you say, well, we know certain things, like we know, everyone above this age is more likely to certain diseases, or below this age isn't, or we have labels on some of the data points, but not all of them needs to be semi-supervised. So you can use clustering approaches on them, but you'd be doing a fusion of them, right? You'd be saying, well, I know certain stuff, so why don't I use the labels I have to learn some kind of model, and then maybe do clustering ideas on top of that. So it's just a fusion between them. So there's nothing, in a sense, special about what semi-supervised is. It really just means in between these two, and so you could use measures of both. When we talk about unsupervised in a pure sense, we really have nothing, no labels. And in a sense, this is actually rare, right? We usually do know something about the data, but we might have a very small amount of it. So it's important to know what algorithms are possible here, but this is actually, in a way, much more hot area. Like, this is kind of the holy grail, ultimate goal of a lot of people in AI and machine learning, to say, like, we just want to naturally just learn it, because you can imagine this is what animals and humans do, right? They just learn from nothing, right? And they know how to learn languages and all this stuff, but they're not learning from nothing. We have millions of years of pre-trained rules and biases in our head. So essentially, even babies who learn incredibly quickly from very small amounts of data have labels of some kind. At least that's the way I think about it right now. Yeah, so if you have some of the information, it could help you set things like how many clusters to use, for sure. So that is important to point out. But let's go through it so people know what these algorithms are, because we haven't actually introduced them yet. Representations, I've mentioned some of this already. So it could be logical rules, but we're going to be talking about things where it's these sets of points. So what are we talking about here? This is just the main idea that we're going to be using distance between points, right? So a measure of dissimilarity, we're usually going to be calling it. So we're calling it, which is, like distance is another way to talk about that. If they're far apart, then they have a high distance or a high dissimilarity. Obviously, similarity would be the inverse of this, right? And if your similarity is high, then your distance is low. So that's just words. Just make sure you're using the right one. If someone asks for a similarity score, don't use a distance score, at least invert it somehow. But they're all coming down to this main idea that points that are close to each other seem like they should be in the same cluster, right? That's easy. But then sometimes points that are close to each other should not be in the same cluster, and that's hard. So how do you determine which it should be, right? And that's kind of that first category of things is what we're going to talk about. So we're going to have two concepts here, which are not really complicated, so we'll kind of go through it a bit quicker to get to the more interesting algorithms, but we can come back to it if people find it confusing. A lot of it's just very subtle English word differences, so I can understand that might not be the clearest. But the main idea, and it'll be more clearly shown on the slide in a minute, is that we're going to be talking about the distance between clusters and within clusters of points. So just to define what inter and intra means, right? All right, so we've got some data points, and we've got two clusters that we're going to be labeling as A and B. We're assuming these are the correct names for them. And intra-cluster are the points between the distances between points in the same data set. Right, and then we talk about intercluster, so like interdimensional, rift, I'm writing interdimensional. What's another? International, right? We talk about, what's the distance between two clusters themselves, right? An intracluster is the distance between points within it, right? So this means more like within, and inter means between. I guess that's the real English meaning for why we're doing this. Intra means that, and inter means between. Okay, so all right, so we're going to have two of these fundamental algorithms approaches to building clusters. We're essentially going to build trees by iteratively putting them together or taking them apart. And we'll call them agglomerative and divisive, but they both have the same idea that essentially, well, I'll show, there's a picture here a couple slides ahead, which is better. Agglomerative algorithms, we have a bunch of data points, and we say, are these points close together? Yes, these guys are nice and close, so we're going to group them together into one class. I went too far there. And then once we decide then what the next point is, we're going to say, oh, these points, the next closest point will be this one, and so we're going to have add them together that way. And so we build up clusters by finding points that are near each other or near to the existing groups and adding them and sticking them together, right? And essentially at some point you cut off how much of these you're doing, and that gives you your clusters. Divisive is the reverse, so you start with everything in one cluster, one big group, and you decide where's the best place to split them. You say, well, these seem to be the biggest gap. This is the largest inter-point gap here between these sets of points, and we'll split it in two. And again, once you can stop and start, how you decide when to stop and start will determine what clusters you have. So this hierarchical approach, that's the main idea between them. And in order to define them a bit more clearly, we have a couple other ideas of trying to gauge these distances between clusters and within clusters. So when we're trying to optimize the single link, it's called, we're trying to minimize the distance between the points in each cluster, right? So we're trying to minimize the intra-point distance, and when we're talking about the distance between the two clusters themselves, you have to say, are you using the nearest points or the furthest points? So in a complete link, we're using the furthest points in the sets to tell us that what the distance between the two clusters are, and in single link, we're using the minimum distance. So we have two sets of points here. We see two different examples, right? So we have two clusters, and we say, well, how close are these clusters together, right? So should we merge them? If we're doing an agglomerative thing, should we merge these clusters of points? And if you're using a single link, so essentially when you define that you're going to run this algorithm, you would have to pick single or complete or some other metric like this to say, given two groups of points, how do I tell whether how close they are, right? Because that's not well defined, right? You could say it's, these two groups of points, their distance is the distance of their nearest neighbors within those groups, right? That's what single is. Or it's the distance of the furthest neighbors, the furthest points from each other in those two groups, right? So you've got to compute the pairwise distances between all these points to figure this out. But these are two different ways you could define the distance between the groups themselves, right? You also obviously could say what's the average point of this kind of the center of these two groups and call that, right? So that's called average link. So they have other ones that basically do the same thing, but they're all intuitive things you could come up with and just say, well, what's some statistic of these points that I can use to compare them? And then this is showing the same thing. It's tricky because you can have some points where some situations where it would change the decision whether you should merge them or split them. So here, when we're using the complete link, the distance between these 2 points are smaller. What are we trying to get at here? Using complete, so they're using the maximum points. So we're saying that this one on the left is less than the one on the right. Oh, from this other data set. Sorry. Right, okay. Yeah, so the other point I'm trying to show here is with the two lines. So say you have, if you're doing agglomerative, right? So we're trying to merge them up and decide what's the next one I should merge. You'd say, what's the two closest groups of points, and I'll merge those, right? And so when you're doing that, depending on whether you're using complete or single, you might get a different answer, right? Because these points are closest to each other given a single link representation, but using the complete link one, you get a different. This one, these would be the closer, because in this case, the next complete link, the furthest points in this one are further away than that. So it really will affect what order you put them together in. But that's the main idea of these agglomerative and divisive algorithms. Right, so the average link is really, as you would expect, just the average of the distances of all the points in those classes. So clusters, sorry, sometimes I'll say class, I mean cluster. So you get all the points in two clusters you want to compare and find their distances and then compute the average distance, and that will be your distance. Obviously this is expensive because you got to compute this distance for all the pairs of data points in your data set. So these are not necessarily the most efficient way to do things, but it's a simple algorithm, well, class of algorithms. This is just explaining divisive. I think there's nothing. Yeah, the only flip on it is that to make it a bit more efficient, you can do the minimum spanning tree. So you could build a graph of all of the points. If you took 606, this is probably something you guys talked about. So you could compute a graph of all the points and then compute the distances between them, and then build a minimum spanning tree, which would tell you what order you should merge in, right? And so once you have that tree, you just use that order to merge them and you're done. Because this tells you the cheapest way to connect different points together. And there's slightly more efficient algorithms to do minimum spanning tree than just this iterative, the naive way of merging them. But you still have to compute the pairwise distances between all the points first. So it's at least n squared in terms of complexity. Right, so here's an example on that minimum spanning tree, so you guys can look at that and make sure it works, but it's not too complicated. Median linkage, so as I'm talking about, if you're doing, you can use the medians or the averages. The centroid is the one I drew there, right? So we take the mean point of a cluster, right? So for a particular cluster, we get all the points, we find the mean, and we're going to talk about distances between means, which is nice, and it's actually a bit more related then to the more popular algorithm that everyone will use, k-means. But one other further addition for this hierarchical approach is Ward's algorithm. It's more of a meta algorithm, so it really just tells you what you have to do in general, but you still have to specify the internal step. So you specify an objective function. Oops, as it happens if I don't use my pen. You have to specify an objective function, and then you just determine if the clusters should be merged or not. And so the ones we've talked about before, the objective function is based on just that single or complete link. But for Wards, let me remind myself. Oh, right, there's a minimization method that you're doing after. So we still have distances between clusters, and you're trying to minimize that. And so if you're using single link merging, you would just put that in as your objective function. But what it does then is it maintains the statistics for each cluster, and then you're trying to minimize the variance. So for each point, you talk about the change. Yes, right. It's error, but it's not error in the sense because we don't have the right answer, but we say that we assume that the mean of the current cluster is the right answer. And so if a data point is really far outside from the mean, I'll have my plus be the mean of some current cluster of points. We could have one that's a bit further away, right? And so his error would be higher, this point's error. And you're trying to decide, well, should it be in this cluster or should it be in the next cluster over, right? And so for all the points, you're completing these errors. And then when you're trying to merge or split, you're trying to optimize the changes in these errors, right? So you can't just take individual points and move them, but you could split it and then merge it again, right? So it does go up and down the tree a bit, but it still uses that hierarchical tree. And it's trying to optimize, like minimize the changes in the errors in a positive way, right? So when you do a split, you'd get a change in the means for those clusters, and the error would change, and you're trying to basically optimize that. So it adds a bit more, not a guarantee, but a bit more structure to this just hierarchical growing up and down, because it lets you go up, either just going all the way up or all the way down for the hierarchical approach. It lets you go up and down, but use this change in the kind of cohesion of each cluster as your rule. But it still doesn't get past the problem that there are complicated algorithms, because they're simple algorithms, but they're complex in time, because there's a lot of calculations you have to do. You really need the distance to all points, and you're kind of optimizing this tree. But they're also limited because you only get to see clusters that you chose in the tree. So if you don't go up and down it, you might miss some opportunities for a better clustering, which is kind of similar to things we would find in decision trees, right? If we weren't able to prune or regrow the tree, we would get into trouble. But it does have an advantage. I don't have advantages listed, is that you can choose kind of smoothly where your clustering is, right? So that idea that once you have all these data points merged, whatever threshold you pick, this could be like, this is like 2 clusters, this is like 4 clusters, you can pick, and all of them are available to you. Once you have this tree, you can choose the number of clusters based on just your cutoff of the grouping of the points, which is nice.